Major, catastrophic failures are almost always preceded by warning signs. In hindsight, they can seem painfully obvious. So here, we're going to break down why those signals are so often missed in the moment, revealing the systemic forces that are really at play.
It's a pattern we see again and again. After a system collapses, whether it's financial, organizational, or technological, the investigations turn up a long history of near misses, of ignored data, and clear signals that something was wrong. And this presents a paradox. If the warnings were there all along, why didn't anyone do something?
You know, the immediate response is often to look for a person to blame, a single operator who made a mistake, or maybe a manager who is incompetent. But the real cause is rarely that simple. Failure in these complex systems doesn't usually come from one big error. Instead, it emerges from a series of perfectly rational decisions made by competent people who are all working under hidden systemic pressures.
To really understand how this happens, we first have to look at the fundamental nature of the systems we build. At their very core, they're almost all operating under a kind of dual mandate. They're trying to serve two purposes that are constantly in tension with each other.
So on one hand, a system has to be productive. It needs to generate some kind of output, meet its goals, and do it all efficiently. But on the other hand, it also has to be stable. It needs to be resilient enough to handle the unexpected and to operate safely. These two goals, productivity and stability, are in a constant tug-of-war.
And this constant tug-of-war creates the system's core tension, that relentless strive for performance set against the need for precaution. It's right here, inside this conflict, that the seeds of failure are planted. We can think of the system as having two main parts. There's the production engine, that's everything that pushes for more output, for faster results, for greater efficiency. And then there are the safety buffers. These are the precautions, the extra time, the spare resources, the rules, all designed to absorb shocks, errors, and anything unexpected.
Now, in just about any competitive environment, the pressure to perform is immense. You've got powerful incentives to get things done faster, cheaper, and more efficiently. And that pressure, well, it inevitably forces people to make trade-offs.
And this right here is the crucial point. When you're faced with a trade-off between getting more done and being more careful, it's almost always the safety buffers that get trimmed. A safety procedure gets skipped to meet a deadline. A maintenance budget gets cut to improve the quarterly numbers. And look, these aren't malicious acts. They are completely rational responses to the incentives of the system.
This slow, steady erosion of safety buffers leads to a really critical phenomenon. It's something that explains how clearly unsafe practices can become totally routine. It's called the normalization of deviance.
The term was coined by the sociologist Diane Vaughan, and it describes a process where a deviation from a safe standard becomes the new, accepted norm, simply because it doesn't immediately lead to a catastrophe.
This cycle usually plays out in 4 steps. First, a rule or a standard is bent just a little bit to meet some performance goal. Second, and this is the most important part, nothing bad happens right away. That lack of a negative outcome actually reinforces the decision. Third, the deviation gets repeated. And finally, after you do it enough times without a disaster, this new deviant practice becomes the baseline for what's considered normal.
To put it simply, what was once an unexpected shortcut becomes an expected workaround, and eventually, it just becomes the accepted way of doing things. The system has lost its original safety margin, but nobody really registers it as a loss because it happens so gradually.
So, as this deviance becomes normalized, the system itself starts sending out signals that it's becoming unstable. The problem is, because the baseline for what's normal has already shifted, these warning lights are often just misinterpreted as background noise.
To understand these signals, we need to talk for a moment about system resilience. Resilience is just a system's ability to absorb some kind of disturbance and return to its normal, stable state. Those safety buffers we talked about, they're a huge part of what makes a system resilient.
So as the normalization of deviance eats away at those buffers, the system's resilience drops, and a stressed system behaves differently. It starts to take longer to recover from even small shocks. There's a technical term for this called critical slowing down, and it actually generates measurable warning signals in the system's own performance data.
This slide really illustrates the difference. On the left, you see a stable, resilient system. Its performance shows a pretty predictable pattern with low variance. When it gets hit by a small shock, it bounces back quickly. But on the right, you see an unstable system, one that's lost its resilience. Its performance is erratic, with high variance. And when it's disturbed, it takes a much longer time to get back to its baseline. The signals are right there in the data.
So why are these signals missed? It's because the normalization of deviance has already redefined what normal even looks like. The people inside the system, they just get used to the increased volatility. That flickering warning light becomes a familiar part of the scenery, not an alarm. The system keeps working, which just reinforces the belief that this new, shakier state is perfectly acceptable.
So now you've got eroded safety buffers and ignored warning signs. This system is primed for failure. The final collapse doesn't require some major mistake or a bad actor. It becomes an emergent, almost inevitable outcome of the system just operating normally.
This is what sociologist Charles Perrow called a normal accident. He argued that in really complex and tightly coupled systems, failures aren't just possible, they're inevitable. They're a normal feature of the system itself that arises from the interaction of multiple small events that cascade in ways no one could foresee.
The final sequence usually unfolds like this. First, a small, common disturbance happens, the kind of thing the system was originally designed to handle easily. But second, the safety buffer that was supposed to absorb that shock has been slowly eroded away. And without that buffer, the small failure isn't contained. Instead, it cascades through all the interconnected parts of the system, triggering a catastrophic collapse.
So when we synthesize this entire process, when we put all the pieces together, we can start to see how failure is often a built-in feature of a system's design.
The ultimate failure wasn't caused by one broken part, one incompetent person, or one massive mistake. The search for a single simple root cause is almost always misleading. Instead, the failure was an emergent feature of the whole system doing what it was designed to do, with all its competing goals, hidden pressures, and normalized workarounds. The accident was, in a very real sense, a product of the system's own success.
And that leaves us with this final thought. The very same rational pursuit of performance that makes our system so productive and so efficient is also what systematically blinds those systems to the slow, silent erosion of their own stability, right up until the moment it's too late.